speaking of the foundations of quantum mechanics, are they inconsistent as they stand in textbook quantum theory?
So if you take textbook quantum theory to be, quantum theory is formulated according to the Dirac-von Neumann axioms. Again, that's Paul Dirac, as he formulated them basically in 1930 in his famous book, Principles of Quantum Mechanics, and John von Neumann in 1932, Mathematical Foundations of Quantum Mechanics. People divide the axioms up in various ways. I'll give a super quick, discussion. They say that to every quantum system, we associate a kind of a vector space called a Hilbert space, a space of vectors involving complex numbers. The elements of this vector space are called state vectors. Loosely speaking, they can also be called wave functions. There's some terminological nuance around that. And these are supposed to represent, in some sense, the state of a quantum system. More generally, you have to use what's called a density operator, which is a little more complicated, but we'll put that aside. And then the next axiom is that as time evolves, these quantum states, whether state vectors or wave functions or density matrices, are supposed to evolve according to what's called unitary time evolution. If it's sufficiently smooth and nice, it can be written as a differential equation, an equation that tells you moment to moment in a Markovian way what each next state will be given the present state. We call that differential equation, when it's for wave functions, we call it the Schrödinger equation. If it's density operators, we call it the von Neumann equation. And then there's all these axioms of measurements. The observable things that you could measure about a system are represented by operators or matrices, these self-adjoint things called self-adjoint operators, matrices. These are the observables of your theory. The possible results you can get when you measure one of them is called an eigenvalue. It's one of the eigenvalues of these operators. The probability with which you'll get that is given by this formula that takes the state, the quantum state of the system, and takes we call it a projection operator, but a piece of this operator. You put them together, it gives you the probability. You'll get that result when you do the measurement. And then once you've done the measurement, this quantum state of the system is projected or collapses to reflect the result and ensure that you'll get the same result if you measure it again right away. Those are the traditional Dirac-von Neumann axioms, and people slice them up in different ways. But I like to think of them as those 5 axioms, right? Hilbert spaces, unitary time evolution, observables as self-adjoint operators, the Born rule for probabilities of measurement outcomes, and then collapse. There are problems with these axioms, not when dealing with, microscopic systems. Microscopic systems, things tend to work out pretty well. And when people say quantum mechanics works just great, they mean microscopic systems. If you want to do a tabletop experiment, an atomic experiment or laser experiment, you're working with tabletop systems, microscopic systems. The theory works great. If you limit yourself to these particular examples, what's the problem? If you want to do particle physics experiment, high energy physics experiment, you're building a giant particle accelerator, you're talking about the Large Hadron Collider or something like that. You have beams of subatomic particles that are flying together, and there's debris that comes out. You collect all the debris. These are all microscopic systems. Quantum mechanics makes beautiful predictions about these results. So you're not going to see any discrepancies for these kinds of systems, at least to the extent that the Dirac-von Neumann axioms give a self-consistent description for microscopic systems, which they appear to do. Perfectly empirically adequate description, the theory works great. So what's the problem? Why does anyone have any issue? We talked before in our last conversation, and I talked about this thought experiment that was proposed, I think, originally by Hugh Everett in his long-form thesis in 1956-57 when he was a graduate student at Princeton working for John Wheeler. Not the one he ultimately published. He published a shorter version, but in the longer version, he opens it up with a thought experiment that has since been usually attributed to Eugene Wigner, who was also at Princeton. And we talked about how Wigner had this paper called On the Mind-Body Question in the early 1960s. But in this thought experiment, we imagine trying to do quantum mechanics with a system that is not small. It is not small. It is not ultra cold. It is not, pristine. The quantum system is something big enough to be a measuring device itself, or even an observer. So again, this thought experiment is called the Wigner's friend thought experiment. Wigner is on the outside of a box. The box is perfectly sealed. Wigner is one observer. Inside the box is Wigner's friend. Wigner's friend is also an observer, a big system, but perfectly sealed inside the box. And Wigner's friend does a measurement on some superposed microscopic quantum system inside the box. And now we have a problem, because we can describe the situation in two ways. We can treat Wigner's friend, the person in the sealed box, as a thing that is an observer, that does measurements, and then we're supposed to use the measurement axioms and the collapse axiom. Or because the person's sealed in a box and there is a second observer on the outside who has not done a measurement on the box or the contents, maybe we should treat the box and its contents as not subject to the collapse axiom. And now all of a sudden we have an ambiguity in the middle of the theory. The Dirac-von Neumann axioms are simply ambiguous in this circumstance. They don't render a judgment of what you're supposed to do. And when we spoke last time, I laid out a whole menu of possible things you could do, and each of them leads you down a different road, right, for how you would resolve this problem. So this is just an inconsistency. And I want to make clear here, there's a difference between a theory being unintuitive or exotic or eccentric and a theory being inconsistent. So let me give you an analogy, a real-world analogy. You've got a friend, and your friend is lovable and trustworthy and nice and always there for you, but your friend is eccentric. Okay, what do? What you do is you love your friend, because we all love eccentric people. Like we're all eccentric to some degree. I'm eccentric. We're all eccentric. We like eccentric people. Eccentric people are interesting. They're interesting because they're often surprising and they're creative, and you never know what you're going to get, and it's always very interesting, even if it's sometimes like confusing what they do. But it's okay, right? They're just eccentric.
Right.
We like eccentric people, and we've got eccentric physical theories. Newtonian physics, despite its reputation of being, it's Newtonian, it's classical, it's when everything made sense. There's a lot of stuff about Newtonian physics that doesn't make a lot of intuitive sense, right? Newtonian physics says that a system, a body in motion, will just stay in motion unless it's acted upon by something. It doesn't come to rest. That's very unintuitive.
Right.
We intuitively feel like things should come to rest. Aristotle believed that the natural state of all objects was at rest. And in Newtonian physics, it's just not. You need an explanation for why a thing would come to rest. But there are a lot of other examples like this in Newtonian physics. We have all this intuition about how circular motion should work. We have this intuition that when you're, moving water around in a bucket, that there's a centrifugal force pulling it in. That's intuitive, but that's like not how it really works. Gyroscopes are where all intuition breaks down, right? That's all Newtonian physics. So Newtonian physics is filled with things that are a little bit unintuitive. And things only get worse from there. I mean, special relativity is super unintuitive. We talked about time dilation, the idea that the time progresses differently for observers in different frames of motion, that what we call all the events that are simultaneous, like they're all happening now, our notion of now is relative, and that different people will disagree on which events are now and which events are in the future and the past. That's very unintuitive. And don't even get me started about general relativity. So I love general relativity. I have taught general relativity here. So we have a graduate level course in general relativity, Physics 210. It's like one of my favorite courses to teach. I've been teaching for over 10 years. I learn something new about general relativity every time. I'm always surprised. General relativity, that class is like an eccentric friend. Every time I teach it, it's like you learn something totally new and surprising. And you're like, really? It really works this way? And it really does. So general relativity is another example of a theory that is just really, really deeply unintuitive. I mean, we always set aside like a half hour every time I teach the class just to talk about the weirdness of black holes. And this is just not even like when you start worrying about quantum effects, just like regular treating black holes as classical objects. Black holes are really unintuitive in a lot of ways. And so I'll just set aside half an hour. I'll just open the floor and I'll just ask students to ask me whatever weird questions they have about black holes. Like, student will be like, if I stick my arm in a black hole, and can I pull it out? Or like all these weird things you could ask. Like, what does it look like if I send someone to a black hole? Can they ever come? Like, all these like weird questions you could ask. So general relativity is super, super unintuitive. Jackson level electromagnetism. So one other course I teach is Jackson level electromagnetism. There are a lot of very unintuitive things that happen in electromagnetism also. So it's not that we don't have theories that are eccentric. We do. I should say that all of these theories do have places where they break down. The breakdown in a physical theory is called, well, a singularity in the theory. Singularities aren't necessarily geometric point-like things. They're just places where your equations stop working. Electromagnetism has this famous divergence of the self-energy of point particles. General relativity famously has singularities. Everyone's heard of the singularities of the Big Bang and black holes and various other places where general relativity breaks down. Newtonian mechanics has weird singular behavior in certain kinds of systems. Yeah. Yep. There's a famous paper by Shia in the 1990s on a 5-body system that exhibits singular behavior. And it was originally predicted that this could exist by Poincaré, I think, a century earlier. So, all these theories have places where they break down. And what do we do as philosophers, as scientists, as physicists, whatever? We look at these theories and we go, okay, the theories work in these regimes. Sometimes they make very unintuitive claims or predictions, and we're okay with that. We like weird, cool physics, as long as it's self-consistent. And there are certain places in which the theory breaks down, and we'll need to, either replace the theory with something else if we're lucky. If we're unlucky, maybe we won't find a better theory that will replace it, whatever. Quantum mechanics is kind of like that, right? There are regimes in which you're working with microscopic systems, and quantum mechanics is nice and self-consistent. We don't run into these ambiguities or inconsistencies. It's a little unintuitive in some of these situations, sure. But when you confront something like the Wigner's friend thought experiment and other thought experiments people have proposed over the years, now you're talking not about things being unintuitive. You're talking about a singularity in the theory. You're talking about an inconsistency. You're talking about something where the theory is just broken. No one would say, well, the self-energy of a point particle electromagnetism is just unintuitive. People would say, this is clearly something wrong that we need to fix. And all I'm saying is the same thing is true of quantum mechanics. There are regimes in which it works well, and there are other situations that we can extrapolate it to where things seem to break down. These situations do entail an extrapolation of the theory from microscopic physics to macroscopic physics. I mean, we're assuming you can go from, the level of an angstrom, 10 to the negative 10 meters, that's 10 billionths of a meter, all the way up to a 1 meter scale, the size of a human. To get the Wigner's thought experiment, you have to have an extrapolation of the theory to that size. Either you can do that extrapolation and you run into the Wigner's friend problem, or you can't. But if you can't, well, then there must be some other place where the theory breaks down. And in any event, something goes wrong. And we just have to deal with that. We have to confront that problem and manage it. But I would go a step farther than that. It's not just that the theory seems to have places where it's ambiguous about what it's predicting or where it's inconsistent. The theory also only makes a very narrow kind of prediction, according to the Dirac-von Neumann axioms. So the Dirac-von Neumann axioms, and again, these are the axioms you'll read if you pick up Griffiths's textbook on quantum mechanics, or Shankar's textbook on quantum mechanics, or Sakurai's, all the standard textbooks, Townsend's book on quantum mechanics, Gottfried's book on quantum mechanics, Liebhoff. The theory predicts measurement outcomes. It predicts what you'll see on the readings, on the dials, on the gauges, on the displays of measuring devices. And it predicts the probability with which you will see those readings on measuring devices. You can compute averages in these theories. They're called expectation values, but those averages are definitionally, axiomatically, statistically weighted averages of numerical measurement results weighted by measurement outcome probabilities. We're talking about a very narrow kind of phenomenon, right? A very narrow category of phenomena. The Dirac-von Neumann formulation of quantum mechanics predicts measurements, what happens with measurements. It's a very narrow slice, a very narrow category of phenomena. When we spoke last time, we talked about how there are all other kinds of phenomena that seem to be happening around us. In the deep past, primordial gases mixing in the early universe. Today, birds foraging, people falling in love, all that stuff. There's lots of phenomena that seem to be taking place that all lie, strictly speaking, outside the axiomatic ambit of the Dirac-von Neumann axioms. So what are we to do with this? We either say that Dirac-von Neumann quantum mechanics simply is not giving a complete description of nature, which is kind of sad. And if it's not, where is the outer boundary? Now, there are some philosophers who defend this point of view. Nancy Cartwright is a famous philosopher who has argued that maybe we just have different theories in different domains. The universe is many dappled. There's just like different theories for different things. But it would certainly be an interesting intellectual exercise, and it would certainly be nice if we could extend quantum theory to describe more of the world. If we do that, now we have a job to do. We either have to explain why all these other phenomena are in fact measurements, despite the lack of measuring devices or whatever. We have to somehow show that all of these things are in fact measurements and therefore in fact lie within the axiomatic ambit of the theory. Some people have proposed that. But the onus is on them to show that it really works, and it's not clear that it does. Or we need to somehow extend the theory, change the axioms in order to encompass more of the world. And that's part of what I'm interested in doing. Now, there are people who will say, wait a second, decoherence. What about decoherence, right? I mean, sure, okay, fine. The philosophers, or at least physicists who cared a lot about philosophy, they gave us decoherence, but we have it now. Doesn't decoherence solve all these problems? Well, Bohm certainly didn't think it solved these problems. He introduced decoherence, and it was insufficient. And ultimately, he introduced his pilot wave corpuscular theory in order to actually get a result. The reason decoherence doesn't do the job is decoherence takes a wave function or state vector, more generally what's called the density matrix, a density operator. And it shows that under certain circumstances, when it's evolving, interacting with an environment in the right way, or interacting with a measuring device that's coupled to an environment in the right way, the density matrix will change in a certain way. It'll become approximately what we call a diagonal matrix in a certain representation. We call this a basis. And there'll be some entries on the sort of diagonal of the matrix, and the other entries will be approximately zero. And at this point, we're supposed to say the measurement's been done and there's an outcome. The problem is, there's nothing in the dynamics, not in the Schrodinger equation, not in the generalizations of the Schrodinger equation, not in the Lindblad equation, or the quantum channels that you use to describe this. There's no known dynamics within normal quantum theory that singles out one of the outcomes. You still need to apply the Born rule to get a probability out of this, and you still need to apply a projection postulate to single out one outcome. There's nothing in the dynamics that will do that for you. And if from time to time people have proposed that maybe there's some sufficiently complicated quantum, standard textbook quantum dynamics that will in fact cause the system to single out one outcome, but this is impossible because of the no communication theorem, the no signaling theorem that I mentioned before. Collapsing down to individual states looks superficially like a non-local process. And you can't get a non-local process happening from what we call a local Hamiltonian. And this is guaranteed by the no signaling theorem. So there's definitely something that's just not working here. And pinning all this down, not just hand waving and saying, oh, decoherence, don't ask me any more questions. Pinning this down is a worthwhile exercise. Subjecting this problem to rigorous scrutiny may bear fruit. It has borne fruit already. And I would argue it will continue to bear fruit going forward.